We are going to talk today about random distributions. I'm going to start with a bit of covering some stuff from the last class that we didn't get a chance to cover, and I will talk about the normal distribution and the binomial distribution and about these as random variables. So the properties of probability, which we kind of had to skim over last week, I'm just going to go over a few of the important points from this to make sure that we actually talk about them, and then cover normal and binomial distribution. And these are covered in the book, sections 3.1 to 3.4, and I have lots of examples in here from the book as well. Oops. So recall last class we were talking about probabilities and various logic rules like the union, the intersection, and we started covering those things called Venn diagrams, these circles that can be overlapping, showing you the probabilities of one event happening, another one happening, them both happening, or neither happening. So a couple. Hi, Emily. I take it that means that the sound is working, which is a relief. So mutually exclusive events. These are events that either one can happen or the other happens, but it's not both. So in the case of whether an individual has cancer or not at a given time, according to the gold standard, it's a yes or a no. And the fact that they're mutually exclusive, we can represent in a Venn diagram like this by two circles that don't overlap. And as you probably could, if you thought about it, imagine without looking at the equation that the probability then of one or the other of these, of cancer or not cancer, is equal to the sum of those two probabilities. And if they're exhaustive, such as in this case, then that sum is 1. So if there were a third mutually exclusive, like indeterminate, that's possible, then the sum of all mutually exclusive and exhaustive events is 1. So the sum of the probabilities of all possible outcomes is 1. That's one of your basic laws of probability. And the exclusiveness can be written by this bottom notation, that the intersection of having cancer and simultaneously not having cancer is 0. The probability of that is 0. So exhaustivity and exclusivity. Yes? Exhaustivity means that you've covered all of the possible outcomes. So it's a random event. They're in that you can't predict it in advance, and an exhaustive list of the options is just every possible outcome that can happen in that event. And the sum of all probabilities of all exhaustive options is 1. Now, you can have non-exclusive events. An example, maybe having cancer, having heart disease. If you're unlucky, you could have both of them. And this is represented in the Venn diagram by having some overlap or some intersection of these two circles. So the probability of having cancer is this circle. Probability of having heart disease is this circle. Intersection of the two is this space in between, and the union is all of it together. So now, since these are not exclusive, the probability that the union is not just the simple sum of the two probabilities. You remember on the previous page, the probability of this union was just this simple sum, right? But now because there's this, you're counting that twice if you take that sum, if you add up the area or the probability of this circle and this circle. So you have to subtract it off again. That's because they're not exclusive. That's right. So if you add together your probability of having cancer plus your probability of having heart disease, yeah, then your probability of having both is somewhat less than just the sum of those two. Now, if these are independent events, meaning that they have separate risk factors, your probability of having cancer or heart disease is independent of whether you have the other, then your probability of having both, the intersection, is just the product of the two. And you got some practice with that already last week in the lab, how your probability of rolling 2 6s in a row is a sixth times a sixth. This is just a formal statement of that your probability of independent events is a product of their individual probabilities. So can you tell me something about this probability, cancer and heart disease, relative to the probability of one of these, say of cancer, whether it's more or less? What's that? Why do you say it would be more? So they're not exclusive events because you can have both of them. They're independent events, which means that the probability, I mean, in real life maybe they're not, but in this example they're independent events. So probabilities, you'll remember, they're always between 0 and 1, right? And they might be 0 and they might be 1. So your probability of both, or the product of them, is going to be less than the probability of one of them. Unless one of these is 1, then it'll be the same, because that event happens for certain. If they're not independent, then you have to replace this statement here. Instead of just probability of cancer times the probability of heart disease, you can replace it with probability of cancer conditionally on having heart disease times the probability of having heart disease. So that non-independence just means that this conditional probability doesn't simplify into this marginal probability. Are those terms starting to sound a little normal to you? The conditional probability, the marginal probability? Good. Can anyone tell me another way to write this term on the bottom? What's another way to write out the probability of having cancer and heart disease if they're non-independent? This is one of two alternatives for which conditional probability to use. Maybe you can tell me how you would read this in plain English and then tell me the alternative. Yes? Close. So I think what he said was probability of having heart disease given that you have cancer times probability of heart disease, which, that's right, cancer. Yeah, that's right. Yeah, here, I'll write this on the slide. So it's also, oh, and we have an answer coming across, and that answer is correct. I will go ahead and say that. Yes, that is correct, Emily. And I'm going to write that out on the slide too. Probability of heart disease given cancer times probability of cancer. So when you say it out in English, it makes sense, right? That your probability of having heart disease and cancer would be like your probability of heart disease given that you have cancer and times the probability of having cancer. Or the other way, your probability of having cancer given that you have heart disease times your probability of having heart disease. Yes, times the probability of having cancer. Yeah, the first one is probability of having cancer given that you have heart disease times the probability of having heart disease. Yes, question. Good question. So the question is, does this part change? And the answer is it doesn't matter. So just like multiplication, it's commutative. So 3 times 2 is the same as 2 times 3, and you can put this in either order. Your probability of having cancer and heart disease is the same as having probability of heart disease and cancer. It's the same thing. Yeah, let me see. Do I have any? Okay. I don't know if I can come up with. I mean, I could just make up examples and multiply them, but I think that it would be kind of artificial to try and just write down some numbers here. I mean, I would need the time to actually probably write down where it makes sense is when you're given like, a prevalence or a 2x2 table, something like that. If we have some time at the end of class, I can go over one of the examples that we have. Mm-hmm. Mm-hmm. All right. I want to make sure we get through lecture first, but it would be a good thing to go over during tutorial this week or during office hours, and I'll have more office hours. So why do you call it non-independent rather than dependent? So I'm calling it non-independent here because the probability of having heart disease is not assumed to be independent of whether you have cancer. It's non-independent because I'm saying that this conditional probability is not necessarily the same as this overall or marginal probability. So that's why I say the probability of having cancer is not independent of whether you have heart disease. That's why I'm calling it non-independent.
Just for this particular case,
for this particular case, I mean, anytime if your conditional probability here is not the same as your overall probability, then they're not independent. This saying that the probability of whatever A given B is not the same as just the probability of A means that A and B aren't independent. The probability of A happening depends on B. All right, your probability notation cheat sheet, just so you have it with you. Union, intersection, complement, conditional probability, the joint probability or the intersection, and the marginal probability. Lots of fancy words that have a simple meaning. Okay, so unless there are more questions about that, and I can take some more quick questions, I'm going to go on to random variables now. So by a random variable, what do I mean by that? I mean any variable where there's uncertainty in the outcome, and this is what statistics are all about. We are observing variables where there is uncertainty, looking at an incomplete portion of all of the possible events, and trying to understand something from this random variable and partial observations of it. For example, if we're interested in the number of new diabetes cases in New York City every year, presumably there are some things that would help you to predict that, like the population of the city, how many cases there were last year. You know, there are some things that could help you, but it's at least partially determined by chance. You can't predict it exactly, so it's a random variable. Or the weight of some randomly selected individual. Again, you could make a guess. You could say that, you know, 95% sure they're going to lie within these bounds, but you can't say exactly how much any individual or any group of individuals weighs. It's a random variable weight. And, you know, we've learned about these already, categorical, discrete, continuous variables. But we're thinking them more of as data before, like these were a set of values that we had collected. Now we want to summarize it, we want to view it. We weren't really treating it as a random variable, and today we're going to really get into taking these variables, taking the probability stuff that we just learned, and treating these random variables using probability. And I'm going to be careful about the notation. Please pay attention and point out to me if I ever stray from this, but I want to prevent confusion by consistently referring to random variables using capital Roman letters, and a realization of a random variable using lower case letters. So the weights of New Yorkers, that's a capital X. The weight of one New Yorker, that's a lowercase x. And I'll index those for different individuals using subscripts like x sub 1, 2, 3. By the way, this notation and a bunch of other stuff about notation that can help you to understand the notes is all summarized in the syllabus at the end of the syllabus. I put a lot of time into the syllabus, so I hope it's helpful. So just a couple quick examples. Blood type. What kind of a random variable is that? Categorical. Yep. And it's a random variable because, you know, we don't know what, if we're treating individuals as records, as observations, then all of the blood types in this room are a sample from a random variable of blood types with probabilities that are known from the population. Number of visits to the obstetrician, kind of variable is that? Random variable? Yeah, discrete. Yeah, that's good. And, you know, of course, we don't know, it's random before the pregnancy. We don't know how much it's going to be. That's what makes it a random variable. After the pregnancy, then for any individual, we have a realization, a lowercase x of that random variable. Distribution of body mass index, that is, yep, continuous. Or you've heard it, I think, called scalar or quantitative, all the same thing. It's a continuous variable. So with continuous variables, they can take any value. So we can't actually say what the probability of getting one particular value was. Remember, with the blood types, we could say your probability of being type A is this, and that's because it was categorical. With a continuous variable, you can't say that because the probability of getting any one exact value is 0, because there are an infinite number of values you could have. But what you can quantify is the probability of getting a value in a certain range. So we're going to be doing a lot of looking at the probability distributions of a continuous random variable. And so that gives you the probability for any given width of this. If you look at that area under this curve, it'll give you the probability of having a realization of this random variable within that region. And the shape of this is, there are different shapes that are possible. We're going to be talking about the ones that look like this, the normal distribution. So the x-axis here is the value of the variable. So if it's, units of BMI, units of weight, kilograms, things like that. And on the y-axis will be a probability. And again, we're interested in intervals, so sections of this curve like you see shaded here. And one thing to remember about these is that the total cumulative probability has to be 1. Because if you look at all possible values along this x-axis, you're getting an exhaustive coverage of the values that random variable can take, and the sum of the probabilities, if they're of exhaustive events, is 1. So that's what we're going to cover first, the normal distribution, and then we're also going to cover today the binomial distribution, which we use for binary events. So things to know about the normal distribution: it's symmetric. So you pick the midpoint, then it's symmetric about that. It's a mirror image. It's bell-shaped, just meaning that it's highest in the middle and it goes down towards 0 on either side. And it's characterized by just 2 numbers, a mean and a standard deviation. The mean is where that center is, and the standard deviation tells you how wide it is. And you'll notice, so here are 2 different normal distributions. The first one has mean 0, standard deviation 1, and the second one has mean 19, standard deviation 4. But you notice they look exactly the same, right? So that's something that you should know about the normal distribution, is that it's just one distribution. The shape is always the same. So if you move it so that it's centered in the same way like they've done here, and you scale it so that it looks like it has the same width, even just by showing different values along the x-axis, then they look the same. Even if you were to put those two distributions on the same x-axis, they would look quite different. So here's that first one with mean 0 and the other one with mean 19. It's wider and it's shifted further to the right. So that's an important thing that you're going to do a lot of. You're going to take a variety of normal distributions with different means, different standard deviations, and you're going to standardize them using something called the z-score and turn them all into the same distribution with mean 0 and standard deviation 1. Yes?
More, you're saying instead, because it's 4 standard deviation is 4, that's much more if you stretch out further. Versus there's only 1 standard deviation, only 1, so it's less to be stretched.
Yeah, so the one on the right is wider, more dispersed, because it has a larger standard deviation, or it has a larger standard deviation because it's wider. The mu, the mean, tells you where the middle is, and that standard deviation tells you how wide it is. So here's an example, a couple different standardized tests. These are popular examples because they tend to be designed so that they will have a normal distribution with known mean and standard deviation. So the SATs, this I guess would be the sum of the three. Apparently the mean is 1500 and the standard deviation 300. And this ACT, mean of 21 and standard deviation of 5. So two different normal distributions. Anyone know which one this is? Which test did Anne take here? Yeah, that's the SAT because it's centered on 1500, has, standard deviation of a few hundred. And Tom took the ACT because it's centered on 21. So as I mentioned, standardizing with z-scores. This is what lets you compare the relative position or probabilities from two different normal distributions. All you have to do to convert a realization of either to convert any realization from a normal distribution to the corresponding z-score, or to convert an entire random variable to the standard normal distribution, is to subtract the mean and divide by the standard deviation. That distribution will then have a standard deviation of 1 and a mean of 0. And that's the standard normal distribution. So here's a question for you. Suppose that we had gone and done that with this distribution. We did that z transformation. Would we end up with a standard normal distribution after we subtract the mean and divide by the standard deviation? Would it look like that? Does it convert this skewed distribution on the right to a standard normal distribution that would look like the plot on the left? Anyone? Yep. That's right. The answer is no, because it's not a normal distribution. The z transformation converts any normal distribution to the standard normal distribution, but they're still normal before and after. If it's not normal before, it won't be normal after. Yeah. Yeah, so this standardization with the z-score, it converts any normal distribution to the standard normal distribution. To the normal distribution that has mean 0 and standard deviation 1. But it doesn't make some distribution that is not normal into a normal distribution. Sometimes there are other ways to convert a distribution into a normal distribution, but we're not going to worry about that. So if you convert the entire random variable to using this z standardization, that's a standard normal distribution. If you convert one value, that its corresponding trans-standardized value is the z-score. So what about these two examples? We can calculate a z-score for Anne and for Tom, and then we can compare them directly. We can say, did Anne do better on the SAT than Tom did on the ACT, even though they're different exams? We can still say which one did better than the other, and it'll be in terms of a percentile. So let's see. For Anne, z something like 1800 minus 1500 over 300. For Tom, it's 24 minus 21 over 5. So this is 1, and this is 3/5. So who did better relative to their peers? Anne. Yep. And we will get shortly now to saying just how well each of them did to their peers. And for that, we're going to need probability tables or the empirical rule. And we have some questions here. Let's see. You guys need to let me know when there's a question if I miss it right away. Sample is compared to population, in other words. Oh, I guess I was probably talking about the z-score versus the standard normal distribution. And yeah, calculating the z-score, we're talking about observed data, a sample. The standard normal distribution, that would be the population. That's like that's a population distribution. Let's see, what does x represent? Oh, here, x represents a continuous random variable. So it represents, this is a continuous random variable, e.g. BMI, weight, that sort of thing. Oh, thank you. Okay. So we want to actually say how well was it Anne and Tom did on this test. We're going to do that in terms of quantiles or percentiles. And if any of you had to take the SATs, you'll know what percentiles are. It's how your score was relative to the rest of your peers. So once these scores are converted to z-scores, we can then use this standard normal distribution to calculate probabilities like this. So the percentile or the quantile would be the probability of scoring at that z-score or anywhere below. That's the percentile or the quantile. And we have tables. Our book, not all books do this because you don't actually need it, but our book makes it a little bit easier to look up z values by having separate tables for positive values of z and negative values of z. Anyone want to take a guess as to why you don't actually need this, why you could just get by with one of them? What would you do if you only had a table for positive z's and you needed to look up, and you needed to look up, say, this value of z? How would you do it? Sorry? Subtract from 1? Yeah, you remember, you take advantage of that property that the normal distribution is symmetric. So the area to the left of here is the same as the area up here. So if you were to look up the probability, the so-called left tail probability for this positive value of z, and you get what's this shaded area, and you go 1 minus that, then that's the area that's unshaded here, which would be the same as this area on the left. You'll get practice with this. And anyways, you do have the two tables, but I want you to get accustomed to, one of those probability rules that you should just internalize and be really comfortable with is that the sum of the probabilities of all possible events is 1. So the sum of the probabilities of having a z score less than a given value plus the probabilities of a z score greater than that have to sum to 1. So let's look up, for no particular reason, z equals 0.43, just to quickly show you. Actually, I'm going to go through this pretty quickly because you will get plenty of practice with this in the lab in the assignments. But this is what your standard normal distribution table looks like without the shadings. The shadings are here as a hint to you. If you want to look up 0.43, you look up 0.4 on the row, go over to 0.03 in the column. So you add them together, and whoops. And there it is. So this is actually, if you didn't know whether this was the left tail probability or the right tail probability, what would you guess it is? So for 0.43, we're getting 0.6664. Is that to the left of 0.43 or to the right of 0.43? To the right, you think? So let's say this is 0.43 here, and we're getting a value of 0.66, something over a half. Remember that the probability to the left of 0 is a half and to the right of 0 is a half because it's symmetric. And so the probability to the left of something positive has to be more than a half. So the fact that this is more than a half, 0.66, means that this is a left tail probability. That's the probability of getting z equals 0.43 or less. So far, so good. And just to note, you can also look things up in the other direction. If you had been asked, you know, what score corresponds to the 66.6 percentile, you would find 0.666 on here. You would see that it's a z-score of 0.43, and then you would potentially go in the reverse direction of a z-score back to the original scale to get the SAT. You could calculate what is the SAT score corresponding to 66.6 percentile, or what is the ACT score corresponding to that same percentile. Yeah.
Back again, when you got that number again, I'm just trying to visualize. Say in terms of value, it was to the left too, or is in terms of standard deviation? I thought I got it.
Okay, so what I was saying there is we're looking up a probability for z equals 0.43, and sometimes there are tables that are to the left of a given value, like ours, but sometimes there are tables that are to the right of that value in different textbooks, and you can tell which it is just by the fact that for a positive value of z, it's more than 0.5. So it's got to include so it has to include more than half of the probability distribution. That's all I was saying. That, you know, whoops. Probability to the left of 0 is a half, and to the right of 0 is a half. So for a positive z value, the probability to the left of it is more than a half. Any other questions? So that table of the standard normal distribution is super useful. You can use it to look up any probability on the standard normal, as long as it's not, you know, too extreme. If it gets too extreme, then you're going to have to say the probability is 1 or 0. But the empirical rule is kind of handy for certain special values of z. It's just a kind of a thing that will allow you to do a quick calculation in certain cases without having to look at the table. You could get by without knowing the empirical rule at all, as long as you knew how to look up values in that table of the normal distribution. But all the empirical rule is, this 68, 95, 99.7 rule, is that between one standard deviation above and below the mean, the probability of a value in that interval is 68%. Between plus and minus 2 standard deviations, that's 95%, and plus and minus 3 standard deviations, that's 99.7. So this, by the way, is a way, if you just have a string of values, that you could tell more or less whether it is normally distributed, because you could calculate the mean and standard deviation and calculate what those intervals are and how many of your values lie within each of those. And that actually is a test of normality. You don't need to do that. But this is just to say that if a distribution is normal, it will follow the empirical rule. Approximately. When you have a sample, it's not going to be exact. If you had a very, very large sample, it would become closer and closer to exact. So if you're on the scale of the standard normal distribution, then it's just values of 1, 2, 3, but you can use it for on the original scales, such as weights and heights. And here's an example of going from the z-score scale back to the original scale by actually taking the mean and adding the standard deviation to it. And I'll leave these for you to look at. And these are super typical questions for homeworks, for exams, just given various different intervals asking you to calculate probabilities. So here are some steps for you to go through anytime you have a question like this, stating your problem in terms of the random variable and the realization, doing that standardization step to state the problem in terms of z. Drawing a picture is a really useful thing to do to make sure that you're using the table correctly and not getting confused by the question. As soon as you can draw it on a standard normal curve, then you'll be able to write out what the probabilities are that you need and do your arithmetic. Because we might not always just ask you for something that is under one tail, you know, like it might not just be, you know, everything, but we might actually give you two limits and say what's the probability of a value between those two limits. And if you can draw it out, then you can do this in terms of, you know, you remember that the probability of everything is 1. You need to subtract off what's under this tail, and you need to subtract off what's under that tail. Or alternatively, maybe you do it by calculating everything to the left of this value and then subtracting what's in this left tail. But with a little bit of practice and drawing it out like this, it's going to be no problem. And then finding the area, I'm starting you out with this in sort of academic situations because it then extends to all of the hypothesis testing that we're going to do this semester. It turns out that hypothesis tests are really about calculating a random variable that we know, like the normal distribution. We'll do other ones like the chi-square distribution, the t distribution, and transforming our values from our sample to a realization on that distribution and calculating a probability under a curve just like this, looking up that probability just like this, even if it's a different distribution. So this is a very general type of procedure that we're learning right now.